Right, hello and welcome. In this video, we're going to look at this band pass filter. This is going to incorporate both inductors and capacitors, and what we expect from inductors, them liking lower frequencies, and what we expect from capacitors, them liking higher frequencies, are going to combine together in this example here. So the first thing we want to do is determine our output voltage, and we actually do that by understanding how this is going to function. We're going to have a very specific frequency where these two, the push from our inductor and the pull from our capacitor, are going to balance each other out, and we're going to be left with no nonlinear resistance in the circuit. And so we can just assume that the output voltage, when we're at resonance frequency, when we're at the very specific frequency where these two cancel each other out, that we're just going to be left with linear resistance. So we can use a voltage divider equation for our V out. We can say V out is equal to the voltage divider. We know that's what we want divided by what we have, and we want to know the output voltage across this resistor. So we'll put R1, our 100 ohm resistor, on top, and on bottom we'll put our RT. And in this case, we have winding resistance for our inductor. Because our inductor is a wire wound component, we're going to see that it has winding resistance that we have to account for. And so in this case, we'll say that our total linear resistance would be the winding resistance plus the linear resistor here, the 100 ohm. So we'll add those together on bottom, and that would be our RT. We'll consider RT equal to 110 ohms. So at this point, we can multiply this by our voltage source of 10 volts, and that will give us the output voltage that we expect across that resistor. We'll plug that in over here. We have 100 on top, divided by 10 plus 100 on bottom, multiplied by 10 gives us 9.09. And that is our output voltage that we expect, 9.09 volts at resonance. So now we've got to figure out what resonance is, what that frequency is where the inductor and the capacitor balance each other out. And that's found using our center frequency, FO. FO is equal to 1 over 2 pi. That 2 pi there represents that circle rotation because 360 degrees is 2 pi in radians. So 2 pi square root of LC. And we have all of those. We know what our inductor is and we know what our capacitor is, so we can plug that in. We can say that we have 1 over 2 pi times the square root of L and C multiplied together. And we know our L there is 1 millihenry, so we can type that in by moving that decimal point over, 0.001. We'll multiply that by our capacitor. That one's really small, so 2.2 times 10 to the negative, it's nano, so we'll do 9. And that's going to give us our frequency right there, 107,302. We can round that off. We can say it's 107 for our center frequency, 107.3 kilohertz. And that's what we'll set our frequency to in our circuit here. So we'll double click over here, and we can set, instead of 10,000, we'll say 107.3 K. And that's going to be our center frequency. Okay that out. From here, we can use that frequency to determine our XL, and we know that XL is the inductor's resistance, and so we can plug that into our XL equation. XL is equal to 2 pi FL. So 2 pi is that rotation of the circle. Our frequency, specifically FO for this one, our original cutoff frequency there, and then our inductor value. We can plug that in to our Desmos. Say that we have 2 pi times the cutoff frequency, that's 107,300, and we'll multiply that by our inductor value of 0.001. So we're left with an XL value. So XL is now equal to 674, and that's in ohms. That's our inductive reactance for that inductor. And so now that we have that, we can use that to determine our quality of this filter. And our quality is Q. It's a quality factor, so it doesn't have an ending on it. It doesn't have millivolts or anything like that. It's just going to be a factor of nonlinear to linear resistance, specifically XL and our RT, right? Nonlinear and linear resistances. And so we can plug that in and say that we actually have 674 for our XL in ohms. We'll divide that by 110 for our total resistance. We found that earlier. And we can figure out our quality factor for this one. So say 674 divided by 110. We can round that one up. We got a quality factor, Q, equal to 6.13. And again, it's a factor, so it doesn't have an ending on it there. At this point, we can use that to determine our bandwidth for the circuit. Our bandwidth is equal to this quality factor. So BW equals our cutoff frequency, our center frequency, divided by our quality factor, our Q. So we can plug that one in. Set this one out, and we can say that our frequency is 107,300 divided by 6.13. And that gives us 17.5 kilohertz. So write that, our bandwidth is equal to 17.5 kHz. So that's what we expect to measure. So I'm going to remove some of these calculations up here, and we can measure that out and see if we got it anywhere close here. Drop out all of these, and our Q factor here, we don't need that one anymore. We just need our bandwidth left over, really. And now we can grab our Bode plotter out. That is the fourth one on the side, or the sixth one on the sidebar over here, or you can go to Simulate, Instruments, and get your Bode plotter that way. This Bode plotter measures the input to the output. And so on the positive side of our input, we're going to go towards our voltage source, so the positive side of our voltage. The negative side goes to the negative side of our voltage, or ground. We'll plug that in over there. The output is going to go around our output for our resistor, and they gave us these two lines here to signify that. That's going to be where we plug in any other external circuitry after this as well, like a speaker. So the positive goes to the positive side, the negative goes to the bottom side of our resistor, or the negative side of the circuit. That's technically all the way across the bottom here as well. We'll plug it into the end over here just to keep it consistent. We don't need to change any of the colors of these wires because we're going to get one single line out of this Bode plotter. So let's double click on that. And we'll hit play right away and see what the Bode plotter does without us changing anything. It's kind of off center here, and so we can plug that in differently. We can say that let's make this resolution slightly different. We can put 500 kilohertz here, and then we can increase this up to 20 kilohertz, and that's going to center it a little bit easier. There we go. So now we want to go to the middle of our peak, the very, very top peak here, and we'll watch our decibels on the bottom here. Our frequency starts off really small on one side, starts at 20, that's what we put it at right here, and it should go all the way up to 500 kilohertz. And if we run our thing all the way over to the other side, we see it stops at 500 kilohertz. So that's our scale. And so we want to examine when our center frequency happens, and we see that our decibels, this other number over here, is starting at negative 26 on this side here, and it goes smaller and smaller and smaller until it gets to 0. About 0, and then it starts to grow again. Right? So we're going to right click and go to the maximum peak, and we should find that this is right about our center frequency, 107 kilohertz, and that's about what we got up here. So our decibel range is at negative 0.829, and that's as close to 0 as we're going to get. So we need to add negative 3 to this as well, and then we're going to move our pin based on that value. That's going to give us our bandwidth, right? Because we need to know the width of the band that we're allowing through. This is going to allow only a very, very specific frequency passing. So we'll right click our meter, and we'll go backwards to a value, and we'll take what we have there already, and we're going to get rid of the M here, because we want this decimal. We want 0.829, and so we're going to say negative 3.829. That adds 3 to the number that we had at our 0 location. So okay, that gives us this 98.929. We'll write that down. That's our lower cutoff frequency. Lower cutoff frequency is equal to 98.929 kilohertz. So now we can go for our upper cutoff frequency, and that's going to be on the other side. So we've got to grab our line here again, pull it off the center, right click, and go to the next Y max, and that gets us back on that center line, exact same spot we were before. And we're going to right click, and we're going the other direction. Set Y value the other direction towards the upper frequency to the same value. So we'll get rid of this back end here. We'll say negative 3.28829 there, and we'll okay that. So that's going to be the other side of it, 16.397. So we'll write that down as our upper cutoff frequency, 116.397 kilohertz. So our bandwidth, this value down here, is actually the difference between these two. So we're going to take our upper, subtract our lower, and that should be really close to what we expect our bandwidth to be. Let's get our Desmos out, send this one out, and we will take our upper frequency, 116.397, and we'll subtract our lower frequency of 98.929. We're left with 17.5 0.468. We can round that up. Those are in kilohertz, so this output is also going to be in kilohertz. So we can say that our bandwidth measured, BW, is equal to 17, we'll round that up, 0.5 kilohertz. All right, let us know if you have any other questions.